After learning the Gibbs free energy of binary systems, now we're ready to apply this knowledge to construct and understand the binary phase diagrams. In this video, we'll focus on the fully soluble systems. For the systems with a solubility limit, we'll cover that in the next video. So back to the fully soluble systems. Assume we have A and B, two types of metals, and they are fully soluble in each other. Next, let's plot the compositional space and the Gibbs free energy. We start from a very high temperature, let's call that T1, and the T1 is greater than the melting point of both A and B. In this graph here, A and B depicts the compositional space, and y-axis is the Gibbs free energy. Let's draw the Gibbs free energy as a function of B content in the AB alloy. The top curve is the Gibbs free energy of the solid phase, and the bottom one is the Gibbs free energy of the liquid phase. As we learned from the previous video, as you add more B into A, you introduce more randomness until the composition is 50% A and 50% B. Passing this point, as you add more B into A, you actually reduce the randomness, and the randomness is at the minimum again when it's 100% B. The randomness in this AB alloy increases the entropy of the system, hence decreases the Gibbs free energy. On the x-axis, from left to right, you start from pure A, then the B content increases gradually, and to the right end, the composition is 100% B. In this entire compositional space, the liquid phase Gibbs free energy is always lower than the solid phase. That's why the system stays in the liquid phase. Now, let's decrease the temperature of the system to a temperature we call T2. If you remember the formula for the Gibbs free energy, G is equal to H minus ST. When T, the temperature, decreases, the overall Gibbs free energy will increase. Therefore, please bear in mind that in the second energy diagram, the Gibbs free energy is greater than the one in the first diagram. However, due to the limited room we have here, we'll draw all the Gibbs free energy at a very similar level. Here, we'll make some assumptions. We will assume that the melting point of A is greater than the melting point of B. Therefore, when the cooling happens, A, or a rich end of the AB alloy, will come out as a solid first. Let's construct the compositional space and the corresponding Gibbs free energy diagram. You will see that when the composition is 100% A, both the Gibbs free energy of the liquid phase and the solid phase, they are at the same value. However, as soon as you have small amount of B in A, the Gibbs free energy of the liquid phase is lower than the solid phase, and across the composition, except for 100% A, any other compositions will give you a liquid phase. We can summarize what we have here. So it's all liquid phase except for 100% A, in which it has liquid and solid coexisting. Let's further reduce the temperature to T3, and T3 is in the range between the melting point of A and the melting point of B. This is the most non-intuitive energy diagram here, and I hope you can pay some extra attention. Here are the Gibbs free energy curves for the liquid phase and the solid phase. If we sweep across the composition, it seems this part of the solid Gibbs free energy curve and this part of the liquid Gibbs free energy curve are at minimum. Intuitively, one would assume that from the composition A to the crossover, the composition on the left hand side will be solid and the composition on the right hand side will be liquid. Unfortunately, the intuition is wrong. If you have a closer look at the energy diagram, there are two minima here. We label them as A and B. Let's cross out the solid and the liquid we wrote down earlier, since they are incorrect. When revisiting this energy diagram, we'll start from the easy part. In the compositional space from capital A to lowercase a, no doubt it will be solid. Again, from lower b to capital B, no doubt it will be liquid. The part between the lowercase a and the lowercase b is actually tricky. In fact, during this composition, solid and liquid phases coexist. This is because from the crossover point to the lowercase a, there is a tendency to go to the A-rich end. Similarly, from the crossover to the lowercase b, there is a tendency to go to the B-rich end. In this case, we can truly reduce the Gibbs free energy of the overall system. The Gibbs free energy reduction is achieved by the compositional change in both the liquid phase and the solid phase. The change of the composition in the liquid phase and the solid phase drives the Gibbs free energy to the energy minimum. Next is pretty routine. Let's further reduce the temperature to the melting point of B. This should be pretty straightforward and very similar to the scenario at T2. Here are the Gibbs free energy curves for the liquid and the solid phase. Again, across the compositional space, the Gibbs free energy of the solid phase is lower than that of the liquid phase. So the system will be solid except for the point where we have 100% B. When the composition is 100% B, both the solid and the liquid phases coexist. Finally, let's decrease the temperature further. At this temperature, say T5, it is below both the melting points of A and B. And here are the Gibbs free energy curves for the liquid and the solid phases. Across the compositional space, everything will be solid. Since at temperature T3, both the liquid phase and the solid phase can exist across a compositional space. The compositional window is the lowercase a to lowercase b. This is the most interesting, and let's have a closer look. If the alloy composition lies somewhere between the capital A and the lowercase a, then at this temperature, everything will be solid. Between lowercase a and the lowercase b, we have the liquid and the solid phases coexist. If the composition lies between the lowercase b and capital B, then everything will be liquid. Let's use the information we just learned to construct the binary phase diagram. Note that the T1, T2, T3, T4 here, they don't really correspond to the previous T1 to T5. When temperature is very high, everything will be liquid, and when temperature is very low, everything will be solid. In between, we have the liquid and the solid coexist. There are two important lines here. The first one is called the liquidus line. Above the liquidus line, everything will be liquid. The second is the solidus line. Below the solidus line, everything will be solid. In between, that's liquid plus solid. Now let's assume a composition marked by the magenta dot and at a specific temperature where the liquid and the solid phase coexist. If you extend the line horizontally, the line will cross the solidus line and the liquidus line, and when it crosses the solidus line, it reads at A, lowercase a, and when it crosses the liquidus line, we can read the composition, that's the lowercase b. The lowercase a and b here is the same as the lowercase a and b you saw on the previous page here in the Gibbs free energy diagram. Let's come back to the binary phase diagram. One thing I'd like to draw your attention to is the shape of the binary phase diagram. It has a lenticular shape. In fact, in any binary phase diagrams that are made of two completely soluble elements, the phase diagram shape will be lenticular. If there is a miscibility gap or there is a solubility limit between A and B, the phase diagram shape will be different, which is the subject of one of the future videos. In this video, we have mentioned a few times that when we have the liquid and the solid phase coexisting, this is the most interesting region. Actually, the composition of the solid phase and the liquid phase deviate from the nominal composition. In the next video, we'll show you how we can use lever rule to calculate the compositions of both the solid and the liquid phases.